Hello, this is the May 2018 paper question 1b. It's a Laplace question. It's part B and it's worth 18 marks, but don't let that put you off. It's not that bad. So it's initial value problem. It's d2x dt squared plus 4 dx dt plus 3x equals 10 delta t, where x of 0 equals 1. That means when t equals 0, x of t equals 1, and x dashed 0. So that means when x dashed of t and t equals 0, the whole thing is 0. Using the Laplace transform method, where delta t is a Dirac delta function, also known as the unit impulse function. There's 18 marks, so you will use the transform tables at some stage in this. So there's a few things you need to be able to understand first of all to be able to use the transform tables. First of all, x as written in this equation is actually x of t. It's a function of t. It is like f of t. It's the same idea, it's just that it's an x function instead of an f function. And all these equations here in the Laplace transform tables are given in terms of little f dash t and capital F of s. So if we have a little x of t, that corresponds to f of t in the tables, and the capital X of s, that corresponds to the capital F of s in the tables. Okay, that's one thing you need to know. The next thing you also need to know is that this here d2x dt squared can be written as x dash dashed t. It's a second derivative of x with respect to t, but in the tables we will see that as f dash dashed t. And also then dx dt is also written, can also be written as x dash t, and in the tables that will be written as f dashed t. So if we have a look at the tables, there we have f dash t, that corresponds to our x dash t, and f dash dash t, that means the second derivative, and that corresponds to our x dash dash t. And delta t, the Dirac delta function, is just 1 when you do a Laplace transform on it. So then everything on the left hand side is just a function that is a time-based function. You do a Laplace transform on it and you change it into a function that's based on s, and this is where the capital letters come in, capital F of s. Okay then, so to do this question, let's see, I'll just take down this part here only and start at this. So there are 3 steps to this question. Step 1, do a Laplace transform. Just do a Laplace transform on every term. That's the L. Okay. Step 2, whenever you do a Laplace transform, all the little x's will become capital X of s. So then we want to isolate capital X of s. Oh, the most important thing about this question is that in the end you have to find x of t. You have to find x. That's the question. Find x, or what it's really find x of t. That's what the question is asking, in case you're wondering. Okay, so isolate x of s at step 2, and step 3, then you do an inverse Laplace. i.e. L to the minus 1 of x of s. The inverse Laplace, and that will bring you back to x of t, or x, as we call it here. So basically, what we're doing is we have a function, it's a time-based function, we do a Laplace transform on it, we get to this, we will get an x of s, then we do the inverse Laplace transform of x of s, and we get back to a time-based function. Now, only 3 steps. This step here may take a bit of work because it may include partial fractions or something like that. So this here could be the longest part, part 3. Okay, so step 1 means we have to do a Laplace transform. So I do a Laplace transform on every single term here. So it's going to be the Laplace transform on d2x dt squared plus 4 times the Laplace transform on dx dt plus 3 times the Laplace transform on little x, which is really little x of t, equals 10 times the Laplace transform on the direct delta function delta t. Now I'm going to change this to make it a Laplace transform on x dash dash t plus 4 times the Laplace transform on x dash t plus 3 times the Laplace transform on x of t plus equals, 10 times the Laplace transform on delta t. Okay, x dash dash t. Right, so what we'll do then is we go to the tables and we can look for the f dash dash t. And as you see here, if you do a Laplace transform on f dash dash t, a second derivative, you get s squared, capital F of s, minus little s, little f 0, minus little f dashed of 0. So I write that down, but wherever I see the capital F's, I will put capital X's, and the small f's will give me small x's. So this here part here now becomes s squared, capital X of s, minus s, little x of 0, minus x dashed 0. And that is all x, the second derivative of x, the Laplace transform of that, plus 4 on the Laplace transform of x dashed t. So here we have x dashed f dash t, little s, capital F of little s minus little f of 0. We will change the f's into x's again. So it's going to be plus 4 on brackets s, capital X of s, minus little x of 0. That's that part, okay, there. And then the next part is plus 3. The Laplace transform of x of t is capital X of s. By definition, it's not really given on the tables. It's not really given on the tables. There's f of t, you do the Laplace transform on it. There's f of t, to do the Laplace transform in it. You could do that whole big integration, but we just call it capital F of s. Okay? So in this case, it's capital X of s equals 10, and the Laplace transform of delta t. So don't let the direct delta function put you off, because it's just 1. When you do the Laplace transform on delta t, it's just 1. Well, that's the area under that impulse. Okay, so then all we do now is we tidy this up. We go back to the initial conditions, x of 0 equals 1. We can put in 1 for that. We'll have to multiply this out as well. X dashed of 0, that equals 0. Little x of 0 equals 1. So let's tidy it up. So this is step 1. This is step 1, doing the Laplace transform. Now, we're at step 2 now. We've done the Laplace transform. Excuse me. And we're going to isolate the x dashed s. So we have s squared x of s minus s times 1 is s minus nothing plus 4s x of s minus 4 times 1 is 4 plus 3 capital X of s equals 10. Excuse me. So now we bring everything that doesn't have an x of s over to the right hand side of the equals, the minus s and the minus 4. And we're left with s squared x of s plus 4s x of s plus 3 x of s equals 10 plus s plus 4. So we're getting there now. We can bring x of s out of this like a common factor. X of s on s squared plus 4s plus 3 equals 10 plus 4 is 14 plus s. Okay, so if we want x of s on its own, it's going to equal, I'll put the s in front, s plus 14, just looks more like the tables, all over this s squared plus 4s plus 3. And now we're at step 3. We have to do the inverse Laplace transform to the minus 1 of x of s. And that will give us little x of t, which is what we're looking for in the question. And that is the inverse Laplace transform of s plus 14 over s squared plus 4s plus 3. Now there are two ways to do this. You could go back and do this the same way that we did part A in this question in another video, you know, saying that's s plus 2 all squared, and do that. But what I'll do in this case is I will just do the partial fractions. So I'm going to try to find factors to this, right? Because it's going to end up looking, we want it to look like something on the right hand side here, so we can just read the tables back to get our answer on the left hand side. Now, this does factorize because s squared plus 4s plus 3, s times s, 3 times 1, 3 s's and 1 s gives you 4, which is the middle one. Okay, there's different ways of doing factors. It's up to you what way suits you. But I basically have two factors here at the bottom, s plus 1 and s plus 3. So I can write this instead as L to the minus 1 of s plus 14 over s plus 1 times s plus 3. It's the same question. Now, what we're going to do now with this is we're going to do partial fractions. Okay. Partial fractions. So I'm going to take the s plus 14 separately away from the Laplace thing for now because we want to get it looking like a over s plus 1 plus b over s plus 3. To do this, I'm just going to multiply across everything by s plus 1 times s plus 3. So that will be, if I rewrite it as s plus 14 over s plus 1 times s plus 3 equals a over s plus 1 plus b over s plus 3. And I multiply every term by s plus 1, s plus 3, s plus 1, s plus 3, and multiply b by s plus 1, s plus 3. This is something, a step you could skip. Now we'll get the s plus 1s cancelling for that. We get cancellations there, and we end up with s plus 14 is equal to a times s plus 3 plus b times s plus 1. Okay, it's basically like a twist there. Now, there are a couple of ways to do this. Just moving the chair there. Paddy will do it by letting s equal numbers. He won't let s equal a negative number because in these Laplace transforms, s is always supposed to be greater or equal to 0. It would work out if you decided to let s equal a negative number, but for now, I'll just let s equal 0. I'll let s equal 0. I'll just decide to choose 0, and that means for one equation, we will get 14 equals a times 0 plus 3, that's 3a, plus b times 0 plus 1 plus b. So that is an equation in a and b. And then if I let s equal 1, then that means that s plus 1 plus 14 is going to be 15 equals a times 4 plus b times 2. So if I multiply this equation, so we have two small equations and two unknowns, simultaneous equations. If I multiply this equation here by 2, I will have 28 equals 6a plus 2b. I'll bring this one below it and I'll have 15 equals 4a plus 2b. That's that one there. And if I subtract them, minus, that's 13 equals 2a, which means that a must equal 6.5, half of 13. So we have our value for a, and then we do the same thing for b. I'm not going to get this all on the one page anyway, but I'll get b in this page. So what we have was, if we use this one, 14 equals 3 times a, which is 6.5, plus b. So 14 equals 19.5 plus b, and that means b must equal 14 minus 19.5, which is minus 5.5. That equals b. Okay, new page. I'll move this up a bit so I can see what we have. Right then. So we now had originally s plus 14 over s plus 1 times s plus 3 was equal to a over s plus 1 plus b over s plus 3. And we have a as 6.5 and b as minus 5.5. Okay. Right, so we can put those values in. So we go back to what we were originally trying to find, the inverse Laplace of s plus 14 over s squared plus 4s plus 3. We're trying to find the inverse Laplace of that, which is now the same as the inverse Laplace of a over s plus 1. And for a we had 6.5, and for b we had minus 5.5. So that now becomes the inverse Laplace of, I'll write this out to get it all together, s plus 14 over s plus 1 times s plus 3, because we discovered that this here could be written as these two factors, which is the same as the inverse Laplace of 6.5 over s plus 1 minus the inverse Laplace of 5.5 over s plus 3. But actually we can take the 6.5 out, and that becomes 6.5 times the inverse Laplace of 1 over s plus 1 minus 5.5 times the inverse Laplace of 1 over s plus 3. Now I'm happy enough with those numbers, because if we look at the tables, we have 1 over s plus a equals e to the minus at. So if we do the inverse Laplace of 1 over s plus a, we will get e to the minus at from the tables. Right? So we can apply this now. So we have L to the minus 1 of s plus 14 over s squared plus 4s plus 3 equals 6.5. And now if we look at this, a is 1 in the first case, so it's going to be times e to the minus t minus 5.5 e to the minus 3t. Now that is it done. Okay, so first of all, we had the equation. If we go back to the beginning of this, we had the equation. We did a Laplace transform and everything. We eventually got x of s here. We factorized it at the bottom. We got it into partial fractions, and we had it looking like this. We still had to do the inverse Laplace in it, so we did the inverse Laplace in it, and we got that. And that is x of t, and that is the answer. Thanks.